So now, yeah, let's look at. I will give a small introduction. I will give a history, history of dynamical systems. Yep. So this is the history. Yep. So let me talk about a little bit of the history. Uh, the sub. Yeah. This is this. Yeah. The subject of dynamical systems began in 1600 1600s when Newton invented differential equation. Okay, so yeah, he explained the law of motion and gravitational uh, yeah gravitation to explain the Kepler's laws of planetary motion. So Newton, yeah, uh, so Newton saw two-body system. Two-body he considered Earth and Sun. So Earth yeah, moves around the Sun. So he solved this system. This system solving this system means so he can find the location. He can find the position at a given time. Yeah, solving this two-body system means he can find any location at a given time, right? He solved this two-body system. Uh, yeah, so and the physicist, then mathematician and physicist try to extend this problem. They want to consider another body, which is moon together, and they want to. This is sun, this is earth, and this is moon. They wanted to extend this problem to three-body problem. So they tried to solve this one, but they were unable to solve this three-body problem. So this problem was very hard to solve. But the Poincaré in mid Poincaré in 1800s, end of 1800s. Yep. So had a different approach to solve this one. So he introduced a new method to obtain to analyze the behavior of the system. So rather than solving equations, he introduced he considered qualitative behavior rather than quantitative behavior. So he without solving the equations of this system, he just analyzed the behavior of the stability of the system. He studied the stability analysis. Then he could obtain he could get and he could explain the behavior of the system. So today, we are going to discuss that method. That method is called geometric approach. Yep, geometric approach. So we will discuss that method today for one-dimensional cases. For one-dimensional case, right? So this approach help, so develop this subject. So I have to point correct. This approach help hugely develop the subject of dynamical system. So he could also explain the chaotic systems, chaotic behavior of a system. So as I said before, yep. So it is very difficult. Uh, we cannot predict the behavior of the system if you have a chaotic behavior. That is, the system is very sensitive to uh, initial value, right? Initial point. So yeah. So if we have time, we will discuss chaotic systems as well in this course, right? So after invention of computers, all right, in 1950s, here this thing here. So the scientists use computers to understand the original problem. Yeah. So for instance, Lawrence. Yeah, Lawrence. So he used computers to discover the chaotic motion of chaotic motion on a strange attack that we will discuss at the end of so here at the end of this course. So this system is three-dimensional system, a Lorentz system. So it has three state variables. So he used computers to understand the behavior of that system, Lorentz system. Right. So okay, let's start our discussion, our study. So that was the history of the dynamical system, and this is the content. Okay, let's start. Okay, this is okay. So there are two types of, as I said before, there are two types of dynamical systems. No, I didn't mention. Yep. So as I said before, there are two types of dynamical systems: linear systems and nonlinear systems. So linear systems were covered in your second year. So now we will discuss nonlinear systems. And again, t is the independent variable, as you know. This if x is the state variable, vector x, and t is the independent. X depends on t. So t could be continuous or discrete. If it is continuous, you will have a differential equation. If it is discrete, you will get a discrete map or discrete, no, difference equation like this, right? Okay. So since differential equations are used in many fields, so we first concentrate on differential equation. That means our variable t is continuous. Right? We start off with that case. Later, at the end of our course, we will consider when t is a discrete variable. Now we consider t is a continuous variable. Then if it is a continuous variable, you will get a differential equation all the time, right? Because t is continuous. Okay, all right. Again, yeah, so, right. Okay, let's consider this system. So this is a second order linear system. Yeah, I think which was learning your second year. So this is ODE of second year ODE. So damp harmonic oscillation. Oscillation. Yep. So okay, let's start it from here. We consider that differential equation, right? So I will put double dot, right? X double dot plus P, another constant X dot, X depends on T, yeah, right? So X dot is the first derivative of with respect to T, X dot, okay? And okay, another constant X. So this is a second order linear ordinary differential equation, right? Okay, let's start off with a linear case, linear equation. So this is a linear second order differential equation. So so this is second order. You can convert this equation to first order system of ordinary differential equation. Can you convert this second order ODE to first order system? So how do you convert this one to first order system? Okay, let's do that. Yeah. So I will introduce two state variables because this is second order, right? The order of this equation is 2, and I have to introduce two state variables. The first one would be, I will take, dependent variable x, x. Sorry, this is not a vector, so x. So this x is a one-dimensional variable, right? X. And x2 would be x1 dot x dot. Okay. If you have nth order differential equation, you have to introduce n number of state variables, n number of variables, right? Here we have second order differential equation, right? So we have to introduce two variables, x1, x2, right? So how do you convert this equation to first order? Yeah, can someone say, yeah, how do you convert this to first order? Yeah, so here x2, yeah, you can plug this one into the equation. So without taking much time because you have learned already, right? So let's plug this one into the equation. Then you will get, yeah, x2 dot, x2 dot, yeah, x double dot is x2 dot, right? Which is same with x double dot. Okay, the x2 I solved this equation for x dot, x2 dot, right? And I will put other term. Okay, this is we had m here, and b x dot I will write in terms of x2 and x1 and x2. Yeah, so I will write other terms in terms of x1 and x2. B x dot is x2. Yeah, x dot is x2 plus here constant k x can be written in terms of x1. Yeah, which is equal to x1 equals 0. Yeah. So I will solve this for x2 dot yeah is equal to, let's assume this is not equal to 0. Then I will put these two terms to other side, minus k over m x1 minus b over m x2. So I express x2 dot in terms of x1 and x2. Shall we express x1 dot in terms of x1 and x2? x1 dot is equal to x2 here, x2. Right. Okay, then I can write this system here. Here, this is a first order system. Again, this one also first order system. Yeah, so I will write, and yeah, I combine these two. Yep, so I write vector notation. Yep, so I will, yeah, first one, and this is first equation, second equation. So I will write these two in matrix notation. So first one x1 dot, yeah, so d by dt. Yeah, so this is x1 first variable, and which is equal to what? Which is equal to x1 x2. Yeah, which is equal to x2. Then there is no x1 term. Yeah, the coefficient should be equal to 0. The coefficient of x1 is 1. Yeah, so, and the other one, x2 dot left hand side of the equation, x2 dot, x2 dot is equal to minus, yep, yeah, so put this coefficient, yep, so minus k over m, and yeah, this is the coefficient of x2, let's put, yep, so minus b over m. Yep, so, I will write this matrix notation condensed form. Yep, so I will put x, we label x1, x2, yep. And I will take that matrix 2 by 2 matrix. I will label that as a minus b over m. Yeah, if I write this one clearly, yeah, x, vector x, the vector, what are the components? x1 and x2, two-dimensional vector, and x dot. So here the independent variable is t. If you want, yeah, you can mention that. I won't mention it. So x dot, if you want, yeah, is equal to a x. So right now x depends on t. Yep. So yeah. So yeah, this one. any system, any differential equation, any linear linear system can be converted into a first order system like this, right? Yeah, so like this, yeah, you can transform your linear system into a system of first order system of first order system of order differential equations like this. Okay, so these are called, yep, so yeah, this one is very important. Yeah, let me mention that. Where's that? Yeah, autonomous. No, later I will mention that. Yes. Okay, let's take another example, physics example, right? Okay, so let's consider this pendulum, right? So this is the general position, the mass of this is m, and this is the general position of t equals t. Yep. So at this time you have, so there's an angle. There's an angle between the vertical and string, which is equal to theta. Okay. Tension of the string. Yeah. So let's apply. Yeah. Yeah. Let's apply Newton's second law. F equals ma. Yeah. So let's apply. Yeah. Then this is theta. This one also theta. Theta. Okay. So when you apply that, then there is only one force. Yeah. Against the motion. Yep. So then minus mg sine theta is equal to m. Yep. So how do you find the acceleration of this particle? Yep. So let's assume the length of this string is L. Then the acceleration is L. Yeah. L theta double. Yep. Tangential acceleration. Yep. Yeah. You can cross this off, and you can get this time. Yeah. Theta double dot second order differential equation. Is this linear or non-linear? Is this linear? Previous one was linear second order differential equation. These are because these are constants. So what about this one? Yes. Is this linear second order or Linear. Why do you say it is linear sine if you have sine theta? So is this linear or non-linear? What do you think? Yes, non-linear. Why it is non-linear? Why it is non-linear? Yeah. Can you explain why this is non-linear? Sine term. Yep, sine. If you write the Taylor expansion of sine, so you will get a lot of yeah. Yep. So this is negative or positive. Yeah. Alternative series. So you get so these terms, these are not linear terms. So therefore, because of this is non-linear. Sine non-linear, cosine non-linear, exponential non-linear, right? Theta, 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 exponential non-linear. Yeah. Sine term is non-linear. It's a non-linear term. Okay, this is a second order non-linear, yeah, ordinary differential equation. Yeah. So then, yeah. So I will convert this one into first order system. How do you do? So because this is second order, yeah, I have to introduce two state variables, theta 1 and theta 2. Yeah, so first one I will take as theta, the second one I will take as theta dot. Then this is theta 1 dot. So can I convert this one to, so we can, this one dot is, okay, can put this one into here. Yeah, theta 2 dot is equal to negative g over L. Sine of theta is theta 1. I express theta 1 dot and theta 2 dot in terms of theta 1 and theta 2. Yeah, sine of theta is equal to theta 1. So theta 1 dot is also equal to what? Yeah, yeah, theta 2. So yeah, so you can convert any order to first order systems like this. But you cannot write this one in terms of matrix form. You cannot write this in matrix form because of this sine theta, right? Because it is nonlinear, but you can convert this nonlinear second order ODE to first orders. Yeah, yeah, first order system of order differential equations. Yeah, you know how to convert that. Yep. So let's discuss this. How do you solve? Yep. So yeah, let's take this. I think in your A levels or in your first year or in your A levels, you solve this second order differential equation. How did you solve? In physics or yeah, in physics, yeah, you solve this equation. How did you solve this? How did you solve? Yeah. So this is a nonlinear canonical. So how did you solve this equation in physics? I think in physics you solve this equation in your A levels. Yeah. How did you get solutions? Okay, let's see. Using small angle approximation. Yeah, that's right. So in your A levels, I think you remember, you may remember. So you assume, yeah, this theta is small, is approximately equal to 0. When the theta is very small, the sine term is approximately equal to theta. Then what do you get? Then you get a system, a linear system. So G and L are constants. G is gravitational constant, L is the length of the string. So this is a constant in front of theta. Yeah. So this is a linear system, second order linear system. So there's all this equation, this linear equation. By assuming the angle is small, very small. So by restricting to small angle theta, so 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 they solve the motion. So this theta should be very small. Theta should be very small. So they they know the location. They know this path. So what about other big part? Yeah, this one. So they don't know, the physics people, A-level physics people don't know the solution when theta is large. So by restricting to small angle, so we are throwing out some of physics of the problem. So we are throwing out some of physics of the problem. Here we don't get these solutions. We only get so we only get this big small angle. So this is the solution to this area. Yeah, small angle theta. Okay. So what about this large angles? So we know that when you increase the energy, if you give us when you increase the energy of this pendulum, so this will be able to rotate a full circle. So we, by solving this equation, we don't get that information. So by solving this one, we get only this the solution to this area, small angle. We avoid this part for large angles. So how do you capture the physics of the problem, entire physics of the problem? So that's why, yep. So we using Pointer method or using our dynamical. So you will learn how to capture the entire physics of the problem. So without assuming, without getting solution to small angle, right? So you will see in this yep. So if you so I think we will discuss is this the full note? So no. So we will discuss later. We will obtain the solution to the entire for all theta, not only for small theta, but also for entire theta. Or theta is between yeah in half. Okay. All right. Did you understand? Yeah. The physics. Yeah. So when you were in A levels, so when you study physics, yeah, they draw the physics of the yeah problem. So they just yeah restrict the this yeah variable to small angle. Yep. So then you cannot capture the entire physics of the problem. Yep. So here we will on the dynamical system. Yep. So we will get yep. So all solutions, complete solution for this problem. We'll capture the entire physics of the problem. Okay. So that's why we may in this course we mainly focus on to study the behavior of nonlinear systems. So this is one of nonlinear systems. So we try to capture the behavior. So behavior of theta uh, for yeah, of this problem. Not only for small theta, but also for yeah, any theta. Okay. So if you yeah, so let me discuss this method a little bit. Yeah, our method a little bit. Okay. So here we have so right. So you converted this here earlier. You converted this nonlinear second order system to a system of two first order differential equation. Yeah, this one. Yeah, this one. Yeah, this one. Yeah. Yeah, what is this? This is the yeah. This one is theta one is theta. Okay, theta two is angular velocity. Okay, theta two is angle. Theta one is theta angle. This is angle, and this is angular velocity. Okay. Okay, let's draw a phase space of this state variables. Okay, yeah. So I'm going to draw this. Let me pick a different color. So this is the angle theta, and this is the other variable theta dot. So first variable is x1. Yeah, so remember, so x1. Yeah, theta one. Yeah, so theta one is the angle. Is the angle with the angle of the string with the vertical line. And this is the other variable